Good morning, class. So far we have learnt about various ADTs, namely the stacks, queues, lists and trees. And today we are going to learn about another kind of ADT which is very popular, especially in practice. And the objective of this ADT is primarily, as we already have seen in all the ADTs, the objective is to put a set of items into the ADT or the object and then retrieve items from the object. Okay. And what is our objective in the process? That whatever operations we perform on the ADT, things are done very, very fast. Okay. Whether it's an insertion, a deletion or modification, this is what we have seen in the context of the binary search tree, priority queue, stack, list, queue, whatever. Okay. So now here today I am going to talk about a different type of an ADT where we keep the size of a table fixed and see if we can kind of retrieve the attributes of a particular item in the table in a very quickly. Okay. We also want to modify the attributes of that particular item or name, and we want to insert new names with its attributes, delete a name and its attributes, and all this we would like to see if how quickly can we do it. The difference here is, unlike the stack or the tree or the queue or the list, here is a ADT where the size of the table is kind of fixed, okay, but it gives us very good performance, and we will see this. Okay. What we have seen, depending upon the to retrieve items from a table, you may say, we could also use what we have already done. The idea is, can we do better? Okay. And we have already seen whether it's in a binary search tree, for example, if you want to retrieve an item, if it's an unbalanced search tree, then the time complexity is as high as order of the height of the tree. Similarly, in a list, for example, if you want to locate a particular item, again it's as large as the length of the list. If there are n items in the list, the time complexity can be order n. Because what we are going to try and do is, can we do better? Okay. The ADT that I am going to talk about, you might have already guessed it, is what is called a hash table. Okay. And we basically use a hash function to access an element from a table. There are two types of hashing, static hashing and dynamic hashing. I am going to talk about static hashing. What static hashing is all about is that the identifiers or names are stored in a fixed size table called the hash table. The address or location of an identifier x is obtained by computing some arithmetic function h on x. Okay. So, h of x gives the address of x in the table. The hash table is partitioned into what we call B buckets, and each bucket can hold a set of S records. So, the total number of items that can be stored in a hash table is SB, and h of x is a function that maps the set of possible integers, possible items into integers between 0 and b minus 1. The key can be anything, any kind of string for that matter. So, we have a table here, we call this the hash table. Let me call this HT. This has indices which go from 0, 1, 2 up to b minus 1. Okay. And our objective is, and it can be such that, let us say these are the indices, each index can store a set of items. Okay. All right. Let me give you an example. It may be a little vague what I am talking about over here. HT is essentially an array, and it consists of B buckets, and the index of these buckets are 0, 3, b minus 1, and each bucket can hold a set of identifiers. Why does this happen? Essentially that if you are, depending upon the kind of function that we have, x is the identifier name, and if I pass the identifier as argument to this function h, it is possible that two identifiers map to the same bucket. Okay. Hashing is very effective, and why is it effective? Because if you look at an identifier which is 6 characters long, there are 26 to the power of, assuming that we are using the letters of the English alphabet, we have 26 into 36 to the power of I distinct possible values for x, but any application actually uses a very small number, fall fraction of these. That is what we are saying is there are so many different possibilities for a 6-character identifier, which is given by the expression t in this view graph, but out of which only in an application you are going to use a very small fraction of them. So, identifier density is defined as if there are n identifiers and t is the total number of possible identifiers, then n by t is what is called the identifier density. Then if there are b buckets in the table and each bucket can hold a set of identifiers, the loading factor alpha is total number of identifiers divided by the total number of items that can be held in this table. For example, let us say I have buckets 0 to b minus 1. In this example, let us say each bucket can hold 2 identifiers. That is what we mean over here, that is S here, and b is the total number of buckets, and that is what you can hold. We define what are called synonyms. If h of I1 is a particular key value, I2 is another key value, identifier value, name value, whatever it may be, I am using all of these interchangeably here, then we say that 2 identifiers are synonymous if both of them hash to the same value. Then we also define what is called an overflow. It is possible that a new identifier I, this has only 2 slots, suppose it hashes to this, then we do not have a space to keep it here because each bucket can only hold 2 items in this example. Then we define overflow when an identifier hashes into a full bucket. Then we call it a collision when 2 not identical identifiers hash to the same value, which is almost like a synonym here. And how do we handle the problem? So, here is an example. We have a hash table with 26 buckets and 2 slots per bucket. Notice the indices over here. The indices go from 0 through 25. And what I am doing is, let us say I am using the first letter of the identifier to put it into the particular bucket. And what have we used? Each slot, for example, is defined by the first letter in the given identifier or key value. So, 0 goes into slot into the bucket 0, A goes into the bucket 0, B goes into the bucket 1, C goes into the bucket 2, and so on. Okay, and Z goes into the bucket 25. And each bucket can host 2 identifiers. So, here I have A and A2, and here in D I have only one element. GA and G are 2 identifiers which are stored in the 6th slot, and then notice that there are a lot of empty slots. This is one thing about the hash table, that you can have, as we said, identifier, the number of identifiers which can be stored in are stored in a hash table, and the total size of the hash table. Notice that we only have 5 identifiers, but we have 26 into 2 slots. Therefore, the identifier density, the loading factor on this hash table is very small. Okay. Now, obviously, what would we like? X is an identifier. Let us say, some variable name called, let us say, I have a variable X non-zero or something like that. Okay, a variable name like this, and this has to be, or an identifier name which has to be hashed into this. Then I also have, let us say, Y non-zero, and so on. I am using 7 characters in this particular example. Now, what would we want? I can have a huge hash table. What we would like is, and so I am operating on this h of x and h of operating with the function, hash function h of x on it. So, h operates on the string, and gives me an index. This, let us say, gives me I1, and this gives me I2. What would we ideally like? If the 2 identifiers, in this case for example, x non-zero and y non-zero are different, okay, they are different by 1 character, all right. What we would like is the hash function should be such that it spreads these keys as much as possible on the table. Why so? If x non-zero and y non-zero hash to the same index, there will be a collision. And what am I going to do? So, maybe I will put x non, suppose it hashed here 0, and I put y non-zero this. So next time if I want to retrieve this particular item, once again I am giving y non-zero or x non-zero, and it will come to this, and then to access y non-zero I have to go through this bucket and look at the second element in the bucket. So what we would like is, if the keys are distributed as uniformly as possible on this hash table, the performance of the hash table can be very, very good. Okay? So the crucial part in this hash table definition is what is called a hash function, which transforms an identifier or a name x into its bucket address. There are number of different techniques, and if you look at Kanuth's book on the art of programming, he has a whole lot of hash functions that he has defined. Mid square, for example, square the identifier, that means you're converting it to the integer, square the identifier, then use an appropriate number of bits from the middle to obtain the bucket address. This is one. Division, divide identifier, that is compute the remainder when x is divided by n. This is the most popular, and that you will also see in the example problem that is given, and use this as the hash address. Folding is partition identifier into different parts, add partitions and use this address. So a number of different hash functions that people have come up with to ensure that the keys in a given application are distributed as uniformly as possible. Another variant, which is not part of beyond the scope of this particular course, is what is called dynamic hashing. As the number of items to be stored increases, the performance of static hashing, because the size is small, deteriorates owing to collision. The hash table must be extendable dynamically, which I don't want to talk about in this course, but you should know about it. Okay? So let's do an analysis of hashing. How good is a hash function? So I'm going to take a particular hash function, assume that there are k items and the table size is n. Then the probability of hitting a free location the first time is 1 minus k over n. Okay? Because there are already k items, and I want to choose one of the locations where the k items are not present. So in general, what we can do is the probability pi of an insertion requiring I probes, assuming that the collision handling mechanism, what it does is, let us say the first time you when you hash this, when you ran h of x for x of 0 and y of non-zero, it came to the same location. Then hopefully the next time when I make a probe, and let us say this is already full, it will distribute it such that this location is not used and it accesses the other locations. Then we have that. So basically what do we have here? Probability is n minus 1 minus k over n, that is what we saw. The second time it has collided with this k by n, and then we assume that it is not using any of them. So n minus k by n minus 1, one of these it has collided, so it is choosing the rest of the locations. And P3, for example, k by n, k minus 1, n minus k by n minus 2, and so on. The third probe, the first probe, the second probe, the third probe, that it hits a free location, and we can define this as for the ith probe. Now let us compute the expectation of this, of the k plus 1th expectation is basically IPI, and if the table size is n and the number of keys in the table is m, then we can find the overall average number of probes that are required to insert an element, number of probes that are required to insert an element, search for an element, whatever it may be. There is a small expression over here which says how you get this complexity, and it turns out this value of E, the expected number of probes, is minus 1 over alpha log of 1 minus alpha. What is alpha now? Alpha is the total number of, m is the total number of keys which are present, divided by n plus 1, and it is called the loading factor of the hash table. Here is an example. Alpha is, let us say, the loading factor. Notice that 0.1 means you have 10% full, 0.25 means 25% full, 0.5 is 50% full, 0.75 is 75% full, 95% full, 99% full, and so on. What do we mean by that? When I look at this particular table, I have only 5 elements out of 52 here. So that is the percentage of items that have been stored in the hash table. What is it giving here is that it is telling me that if the hash table is having only about 10% of identifiers which are present, 25% of the identifiers that are present. This is giving me the expected number of probes. And what is very interesting to see is that even if the hash table is 95% full, if you have a good function such that it redistributes the keys against such that it not using that particular location, then we can see that the hash function gives, for example, even when the hash function, if the table is 99% full, it only requires 4.66 probes on the average, or 5 probes on the average. I want you to compare this with a binary search tree, a balanced binary search tree with a large number of items. Okay, so basically it's going to depend upon, even if you assume a balanced binary search tree, and if the number of items is very large, then the depth is defined by log n. So let us say I have 1024 items, and then I'm going to have 10 steps to identify the to determine the location of that particular element. What is nice about the hash table is, notice that it does not talk about the number of elements, it only talks about the loading factor. What is the loading factor? This is the size of the table, how many items are stored in the table, a ratio of the number of items that are stored in the table to the size of the table. Okay. Now, this is for a very good hash function. Another hash which I just showed you here, this is called kind of linear probing. What we do is it hashes to the same value, and we probe at that particular location. Let's say these are consecutive locations, and we search for the particular element. So, for example, if it hashes to the same value, x non-zero is not what I wanted, y non-zero is what I want. So, it accesses this item and it was not it, and it has to do one more probe to find out what the element is. This is called linear probing. And if we did this, then there are two ways of doing this. In a hash table, for example, so let's say 0 through, let's say I have a whole huge hash table like this, whatever it may be, of size SB, then one kind of hashing scheme, let's say these are the, this is the location at which it hashes to, let us say. So, it can be any number of elements 0 through SB minus 1. Yeah. Then what we do is we run the hash function, it, let us say, maps to one of these. Then what you do is, suppose it's already filled, then you find the next nearest empty location and put the element there. Okay. This is actually called linear probing. This is one way of doing it. Another one is you divide the hash table into buckets like we have done here, through b minus 1, and at each location have what is called a linked list. Okay. So, this is, let's say, the first element in this example. Let's say here this is where we saw it. So, let's say this was x non-zero and its attributes, and then this is going to point to y non-zero, okay, and so on. So, basically what we are saying is we have an array of lists over here. This list need not necessarily be implemented using a linked list, it can also be implemented using an array, which we have already seen. So, you have a hash table which is an array of lists, and whenever there is a collision, it is going to keep on adding a new element to this list. This is a different, this is one type of hashing, it is also using linear probing. Here on the other hand, what you do is you have one long table, and on this long table, if a location is already occupied, then you linearly go down, find out what is the empty location and put it there. So, when you are searching for an element, what do? You search for that particular element, it hashes to this, and then from there you linearly search and find out where the element is. Okay. So, you can do various types of hash functions. So, the crucial property is on designing the hash function. And what is interesting is, suppose we use linear hashing, there is a proof which says that if alpha is the loading factor, then the expected number of probes is this. I want you to look at this table. This is very, very exciting in the sense that again here 10%, 25%, 50%, 75%, 90% and so on, and you find that it actually requires only about 10 probes even when the hash table is about 99% full. And remember that 99% full does not mean that your that the number of elements is fixed. You can have any number of elements, but the identifiers, number of identifiers that are stored in that table, the loading factor can be even up to that much. So, this is something about hashing. Hashing is a very, very powerful technique for storage and retrieval of keys. It has been extensively used primarily because of its speed, and especially if the size of the table can be readjusted. There are algorithms today for readjusting the size of the table. When the table becomes 75% full, you double the size of the table, redistribute the keys with again you need a good hash function which will redistribute it uniformly, and you can show that the amortized analysis of that is just about order 1. So this is something which is very exciting about hash tables. The primary issue with hashing is deletion. It's a little cumbersome because let us say I found this item here, I did not find my item, I have to continue to linearly probe, and once I delete the item there might be an empty slot and we have to worry about this. How do you handle this? So what we have talked about is a special type of an abstract data type, and this is called the symbol table ADT, and it's very popular where you have strings which get mapped into locations, and each key, for example, can have a whole lot of attributes which can be very quickly retrieved. In fact, you can have a hash table of objects. Okay, it's very common. Hash table of function pointers. Okay, they're very common to see in practice, which makes the speeds of algorithms very, very good, very efficient, especially in practical applications. So we'll stop here. This completes the lecture on hash tables.